Afternoon session on demand dispatch and microgrids. And first speaker is Juan Miguel Morales from Department of Applied Mathematics at the University of Malaga. Juan has previously been with Technical University of Denmark, and his research are in operations research interests are in operation research and applied statistics with a broad range of topics. Mathematical programming, optimization under uncertainty, hierarchical and inverse optimization, and within energy, one's interests are in renewable integration and demand response and energy markets.
Thank you very much for the introduction. The title of my talk is Electricity Demand Forecasting and Bidding via Data-Driven Inverse Optimization. First of all, I would like to say that this is a joint work with some of my colleagues. I would like to especially mention the name of Javier Saez Gallego, who was the responsible for running the simulation that we're going to see here today. This is the outline of my presentation. First, given that we have already heard very good talks about what we are doing about the importance of changing the current power system operation, introducing more active distribution network and so on. I'm going to make a very short introduction, a very short motivation, trying to explain, to put into context the methodology that I'm going to explain later. Then I will go into more the mathematics. First of all, I will present the mathematical model that we are going to use to represent an aggregation of price-responsive consumers of electricity. Then I will elaborate on the estimation problem, the problem that we're going to solve to estimate this previous model, this price-responsive customer demand model. Then how we are going to solve this estimation problem, and then I will present two case studies. One is for 1 hour ahead prediction of the electricity demand, of the price-responsive electricity demand. Then I will present another case study that is more related to demand-side bidding. How can we twist a little bit this methodology to be used also for power demand bidding in electricity markets? And finally, I will present some conclusions about the work. Okay, so this is the motivation. As we have heard during these 2 days, the electricity system is probably the largest and the most complex infrastructure that the human being has ever built. It is already very meshed, very complex, and we want to make it even more complex because we want to make it sustainable by introducing large amounts of renewable energy sources. We want to also coordinate the operation of the electricity system together with other energy sectors such as gas and heat. We want to exploit the virtual storage that this coordination can bring to the operation of the power system. We also want to turn the electricity system into the backbone through which we are going to replace the current fleet of vehicles with electrical vehicles. And finally, we also want that the small consumers of electricity participate and help with the operation of the power systems. Within this picture, based on this picture, what I'm going to talk about is about how to make these small consumers of electricity active in the operation of the power system. So I'm going to start with a couple of assumptions. First, the setup of the problem. We are going to consider a pool of price-responsive consumers of electricity, an aggregation of these consumers. This means that these consumers are equipped with the technological means, smart meters and smart controllers, to see the electricity price and react accordingly, react to the electricity price. So we expect that this cluster of flexible consumers will react to this electricity price in such a way that normally, if the price at a certain time instant is higher, their consumption will be reduced, and if the price is lower at a certain time instant, their consumption will be increased. So we are going to describe the model that I'm going to present next to describe this pool of flexible consumers is to assume that this aggregation of consumers behaves as an utility maximizer agent. But this is not actually an assumption, it's just rather a way of illustrating the problem that I'm going to talk about. This means that this aggregation of electricity consumers, the way they consume, the way they behave, is similar to or is driven by a stepwise marginal utility function, in such a way that the more energy they consume, the less is the utility, the marginal utility they get from the electricity they consume. Okay, so it's going to be, their behavior is going to be driven by one of these curves that normally is assumed to be concave.
Marginal utility is the derivative of the utility.
Exactly, the marginal utility. So this is the assumption, this marginal utility function that characterizes our pool of consumers. We assume that it's going to be a stepwise because this is very aligned with current electricity markets, where the bidding curve that demands the consumers have to submit to the electricity markets, normally they are blockwise. Okay, so each block is characterized by a marginal utility and by a block width. Okay, so based on that assumptions, we assume that the pool of flexible consumers, their behavior in response to the electricity price, can be mathematical modeled by means of this very simple linear programming problem. Okay, I'm going to describe step by step the variables. Here we have this UBT is actually the marginal utilities that characterize this curve. So here we have U1 for block 1, U2 for block 2, and so on. Then here this XB are the power consumption, the energy consumption belonging to each of these utility blocks. So for U1 we have X1, for U2 we have X2, for U3 we have X3, in such a way that the summation of all these X gives the total consumption of the pool of consumers. Okay, so this is actually the summation of these X variables, one per each block, gives the total consumption of the pool of consumers. This PT is the electricity price that that enters into this linear programming problem and gives rise to the consumption of the pool of consumers. Okay, so the consumers, we assume this pool of consumers, we assume that they are trying to maximize the utility they get from the electricity they consume, which is given by the marginal utility function, while minimizing the electricity cost payment, which is given by the electricity price multiplied by the consumption. Okay, so then we assume, if there is a very simplistic model of the pool of consumers, that the total consumption of the pool is in between a lower bound for the power consumption and an upper bound, which is represented by this lower bar P and upper bar P. And we also assume that each block of the marginal utility function is capped from above by this given EB. Okay, and it has also as a lower bound, of course, 0. So this is a linear optimization problem, and the idea is that we want to infer from observations this linear optimization problem. So we have measured, using this smart metering technology, we have measured a series of prices, of electricity prices, and the consumptions, the value of the consumption that these prices have given rise to. And based on these two time series, price, consumption, we want to infer a model like this one that represents, as best as possible, how the pool of consumers behave as a response to the electricity price. So in this model, this is the model that we postulate. Actually, our unknown variables, the one that we want to infer from data, are these marginal utilities and these power bounds here. Okay? So we seek, as I say here, we seek values of the U's and the P bars such that they reproduce as best as possible the observations, what we observe, which is the consumption of the pool of consumers that is given that has been given rise by the electricity prices. once we have inferred from data this model, we can use this model actually to forecast the consumption of the pool of consumers, for example, for the next time period, xt plus 1. Okay? So far, by the way, you are more than welcome to interrupt me in the middle of the presentation if there is something that you don't understand. So far so good?
Just clarification, the width of these marginal utility is known or not known?
Yeah, it's known. In the, it cannot, I mean, you have the two possibilities, but in the work that I'm going to present here, is known. And if we want to make this more precise, what we just do is to reduce the width of these marginal utility functions. So we can work with, in principle, we can work with as many blocks of your marginal utility as we want.
Also the number of blocks?
The number of blocks is decided beforehand. I think in the case studies that I'm going to show you is, I think it's 20 for one and 12 for another, but it's something that you choose beforehand. Okay? Okay, so just to mention that since we are not introducing yet any dynamics in this model just the time index is independent. There is no intertemporal constraint here whatsoever, so we can just write also this model like this, right? So summing up all the time periods, and also we want to make explicit, we may want to make explicit that the power bounds that limit the total consumption of the pool of consumer may be dynamic in the sense that they can change over time, as I will explain later. Okay?
The utility can change over time as well.
Yes, the utility can change. In principle, it can change. Okay? And also the power bounds. Why not? Okay?
And X is always non-negative.
X is consumption, so it's, and we are only considering consumption, so it's not negative. Yeah, as stated here. Okay, these variables here, they represent the dual variables of these constraints because we are going to use them for the estimation problem, as I will show right away. Okay, now let's imagine that we have a pool of consumers that actually behave as this problem, this linear programming problem says that they are going to behave. Okay, which we know that is not true because consumers, we don't behave as simple as this optimization problem. We are much more complex when we consume electricity. But let's suppose that we behave like this optimization problem says. Then this is a linear programming problem. Okay, we can, since it's a linear programming problem, it has all the blessings, and then it satisfies a strong duality. So this linear programming problem, if we express this linear programming problem as primal feasibility, dual feasibility, and a strong duality condition, and the observation actually come from this optimization problem, then all these conditions are going to satisfy primal feasibility, dual feasibility, and a strong duality condition, right? The observations are going to fulfill all this. However, we know that we don't behave like this, so there will be some errors. So what we are going to do, and this is the estimation problem, how we are going to infer these parameters u and the bar p's, the power bounds, is saying, okay, since we know that we are making a mistake about the specification of the model because it's too simple, what we expect is that this is dual feasibility conditions, and this is a strong duality condition that we can just compute from this model using these dual variables. Okay? But what we expect is that a strong duality condition cannot be satisfied. So we are going to introduce this duality gap, this variable epsilon t, which is representing the duality gap. The mistake that we make by specifying this model that we know that is not the true model of the pool of consumers. And what we are going to try to do is to make the observation as optimal as possible, which means we are going to try to minimize the summation of these duality gaps. Okay? In such a way that if it could happen that this linear programming problem is the true one, then the result that we get here is that we are able to find the power bounds and the marginal utility in such a way that this would be 0. If not, if this is not a true model, this would be different from 0. Okay? By the way, what we are doing here is what we call inverse optimization. Because basically what we want to do in inverse optimization, what we want to do is to infer the parameters of an optimization problem that gives rise to the solutions. In inverse optimization, what we observe is the solutions, and then based on this observation, on these decisions, on these solutions, we try to infer the optimization problem that gave rise to these decisions, to these solutions.
I have a quick question.
Yes.
So this is it? I mean, you have an upper bound on power, right? So this bound is not going to be uniquely determined from observation, is it?
What do you mean uniquely?
Because it can be much bigger. It's still a bound.
No, because these power bounds, and we will see later, they will have a big predictive power. So they cannot take any value that you want, because otherwise your prediction is not going to be good. So the data is going to tell you how these power bounds, the magnitude of these power bounds. But we can come back to that because I have a slide about that. Okay, so with the observations, we perform inverse optimization. We obtain the parameters characterized in our price response consumers model. And then we use the linear programming problem to predict the value of the consumption of the pool for the next time period, or for the next 24 hours.
Well, since the utility is time varying, how can you do that?
How can you do that, the utility to be time variant?
Yeah. Predict if you don't know the utility of the next time step.
You are going to use because I think this is going to answer your question. How are we going to make the utility and the power bounds time variance? Okay, what we are going to say is that since we know that we are very complex as consumers, of course the price is not the only thing that is driving our decisions. There are many other factors that are driving our decisions. For example, the weather conditions, the hour of the day, our driving patterns, for example, whatever. So what we are going to do is to introduce these other factors through the power bounds and the marginal utility. So we are going to make these parameters time dynamic using these other factors that are time dynamic, such as weather conditions and so on. So we are going to assume, this is an assumption, this can be improved, by the way, this is an ongoing work, okay? We are going to assume that the power bounds and the marginal utilities can be explained as a linear regression of the regressors. Okay, we say that the lower bound, for example, is equal to a linear function of some regressors, where these regressors that we're going to consider in the case study are basically the temperature of the air outside, the ambient temperature, the solar irradiance, the hour indicator, and the past price and load. Okay, so this is a way to make utility dynamic, because when the weather condition change, my utility will change as well. So if this is, for example, the wind speed, if the wind speed is changing, my utility will change. That's what we are assuming. Or if this is the outside temperature and it's very cold outside, my utility will be different than if outside is very hot. Okay, so once we introduce this, what I call auxiliary information, when we introduce this linear relationship, we may have a problem. This relationship, when we are estimating these power bounds, this linear regression, these linear functions, we have to be careful, because we need to guarantee several conditions, several very logical conditions, common sense. For example, when estimating the consumer's price response model, assuming these linear functions, we have to guarantee that the maximum power bound, the upper power bound, is always greater than the lower power bound, because otherwise my linear programming problem is going to be infeasible. Okay, the lower bound has to be always lower than the upper bound. And then also, for example, we need to guarantee that the minimum consumption limited, the lower P, has to be always greater than 0, because we are always considering consumption, so the observations are always positive. So how are we going to insert these linear relationships, while at the same time we are guaranteeing that we are not getting a non-logical relationship between these parameters? So what we are going to do is to robustify those constraints. What does this mean? It means that we want to guarantee, this is an example, we want to guarantee that the lower p is always lower than the upper p. That when we are introducing the regressor here in the linear functions, this is always satisfied. So in order to guarantee this, what we do is to assume use classic robust optimization techniques. We assume, for example, that the outside temperature is within a range. And then, based on this range, we can basically compute the alphas and the mu's characterizing this linear relationship, right? These mu's and these alphas, in such a way that this is always satisfied for all the possible values that my regressor can take. This means that when I'm going to predict based on this linear programming problem, I'm going to predict what my pool of consumers are going to my pool of consumers is going to consume based on the price, right? The power bounds, the upper and lower bounds that we're going to get based on these linear functions are going to make sense. That is, the upper bound is going to be always greater than the lower bound for any possible value of the regressors, of the weather, the solar irradiance, etc. Okay, so now we have the estimation problem. This is the estimation problem, and we have one problem with we have several problems with this estimation problem. First of all, here we have, remember that this is inverse optimization, so we want to estimate the upper bound and the lower bound. And these are the dual variables. So we have an equality constraint. With products of continuous variables. So this is NP hard to solve. This is highly non-convex, and it's very difficult to solve because of this product of continuous variables. So in order to sidestep these products, we are going to propose an approximate method for the estimation of this problem, of these parameters. And this approximate method is based on the fact that we are going to statistically approximate the solution of this non-convex problem by solving instead two sequential linear programming problems. These two sequential linear programming problems, we call them the feasibility problem and the optimality problem. The feasibility problem consists in estimating the power bounds. So we are going to formulate a problem, an estimation problem, to estimate the power bounds. And once we have estimated the power bounds, we are going to come back to this problem. These will be estimated, so they are no longer product of continuous variables because we are inserting here the estimated value given by the feasibility problem, and then we will solve this problem to compute the best value of the marginal utilities. Okay, so this is what I'm going to explain right now. This is the feasibility problem. What does it mean, the feasibility problem? What we're trying to estimate is the feasible region of the linear programming problem that we have seen before, that we're going to use to predict the load in the future time periods. So this feasibility problem is basically penalizing the number of observations that fall outside the power bounds that we want to estimate. In other words, imagine that we decide this, we give values to this P upper bar and the P lower bar. Okay? So we are going to penalize the observations that fall outside, and we are going to reward the observations that fall within this lower bar P and upper bar P. Okay? So how this works? We have this parameter K, and this parameter K basically is telling us the percentage of observations that fall outside the power bounds. If K is equal to 0, for example, if K is equal to 0, so we don't care about these sheep positive variables, right? All the observations, if this is equal to 0, we are penalizing these sheep positive variables, and we don't care about these sheep negative variables. Okay, so this has to be equal to 0. These two here are equal to 0, which means that all the observations are falling outside the interval given by the lower p bound, the lower p and the upper p. If k is equal to 1, then we don't care about this xi positive, we only want to minimize the xi negative, which basically means that all the observations are falling within the estimated upper p and lower p. Okay? Actually, if we put here k very small, k tending to 0, what we are computing through this problem is the median of the data. As we increase the value of k, we are widening the interval, and we are including more and more observations within the interval. Okay? So we use this feasibility problem where we are actually estimating statistically interval. Okay, it's like this problem is formulated very similar to a quantile regression problem. Okay, so we're estimating this interval. Once we estimate this interval, we take the estimated values of the p-bars. Okay, the estimated value of the p-bars, which are linear function of the regressor. So we're estimating actually the mu's and the alphas, and then we insert them into this problem, which becomes linear, and we solve this problem. And this is what we call the optimality problem. The optimality problem is this one. It's basically the previous one where we minimize the summation of the duality gaps, but now we have sidestep the nonlinearity of the product of continuous variables, because here we are inserting the estimated p-bars that we computed from the feasibility problem. Okay, and this one is giving us the linear function of the utility, of the marginal utilities. Okay, so this problem is estimating the best feasibility set that reproduces the data, while this problem is, once we have the feasibility set, we are estimating the marginal utilities to make the observations optimal for our linear programming problem. Okay, so now how we solve this estimation problem, these two linear programming problems, because what we have gained is that we now can solve two linear programming problems, right? And this is they are very easy to solve with many data, so it's a real quick operation to solve these linear programming problems. But in exchange, we have come up with this parameter k that we have to tune. Okay? So how do we tune this parameter k? We are going to tune it using a validation, cross-validation. Basically, what we are going to do, we have the set of observations. Now our set of observations is composed of consumption from the pool of consumers, the prices, the series of prices that gave rise to this consumption, and also the observation about the regressors, the covariates, like weathers, hour of the day, etc. We are going to divide our data set into three subsets: the training set, the validation set, and the test set. The training set is we use the training set for each value of k that we want to test. So we are going now to solve the two linear programming problems for a range of values of k. Okay? And for each value of k, we compute the estimated linear programming problem. Then we use a second set to measure which value of those k's that have been tried is giving us the best out of sample performance, forecasting performance. Okay, so based on the validation set, we choose the value of k that is giving us the best performance, and then we use a third subset, the test set, to actually evaluate the performance of our methodology. Okay, one interesting thing that we are going to see also in the case studies is that k has a very strong physical meaning, or at least that's the meaning that we have seen in the case studies, that when k is tending to 0, as I said before, the p upper bar and the p lower bar slowly converges to the median of the data. I mean, they collapse into each other and into the median of the data. And then as we increase the value of k, the power bounds get away from each other. This means in practice that if k is tending to 1, the pool of consumer is more sensitive to the price, because if P lower bar and P upper bar are equal to each other, this means that the price has no impact whatsoever on the consumption of the pool. As we increase the interval, it means that the marginal utilities have more to say about the consumption of the pool of consumers. So this is the first case study. It's a synthetic data case study, in the sense that we simulate the consumption behavior of a pool of 100 buildings equipped with heat pumps. And these heat pumps are controlled based on model predictive control. And it's synthetic because we are trying to see how the methodology performs based on two different pools of buildings, a flexible one and a non-flexible one. How are we simulating data from flexible or non-flexible pool of buildings? By the comfort bands. So we say that we have a heat pump, and the heat pump has to keep the inside temperature, the room temperature, within a comfort band, in such a way that if this comfort band is the green dashed line here, is not a band, actually it's just a reference temperature, then the pool of building will try to track the reference temperature, and there is no flexibility at all. Okay, so for an inflexible pool of buildings, what we get is that the price doesn't have any impact on the consumption of the pool of buildings, because the model predictive control is just cares about following the set reference temperature. However, as we increase the comfort bands, okay, we make that the pool of consumers are more responsive, the pool of buildings are more responsive, become more and more responsive to the treaty price. Okay? So we have these two sets of synthetic data, and the first thing is the first thing that we observe is what I have just talked about. For the inflexible pool of buildings, K, the best value of the parameter K, tends to 0, because if K tends to 0, the interval becomes becomes shorter, becomes narrower, and there is less room for the price to impact the consumption of the pool of consumers. In contrast, for the pool of flexible buildings, the optimal value of the parameter K is close to 1, because the price has a very substantial impact on the consumption of the pool of buildings. Okay, so we have compared. Here we are using the methodology to predict the consumption of the pool of buildings 1 hour ahead, and it's 1 hour ahead because we use as a regressor the past price and the past load one time period before. Yes?
In the previous slide, the MPC for the flexible building, are you assuming the price is known in advance?
There is a forecast in the price. It's a rolling horizon approach. Okay. There is a forecast of the price that is updated every time step. Okay. So we are going to compare our methodology with the simple persistent model, which is the naive model that every forecasting methodology has to be able to beat. And then we are also using a classical time series model, an autoregressive moving average model with exogenous input. These exogenous input are exactly the same regressors that we use in our inverse optimization approach. The same exactly, if I remember well, is the weather conditions, solar irradiance, hour of the day, past price, and past load. And then to analyze the forecasting performance of these methodologies and the one that we propose, we use the normalized root mean square error, and also the mean absolute scale error, which has nice properties as compared to the mean absolute percentage error. Okay, so these are the results for the non-flex case, and for the flex case, here is just an illustration of the actual load. Okay, for the flexible pool of consumers, which is the black line, and then the blue line with triangles is the one given, the prediction of the load given by the time series model, while the dark blue line with the circles are the prediction given by the inverse optimization problem. And here also in red dashed lines and green dashed lines we represent the power bounds that are estimated by the inverse optimization problem, because these power bounds are also very meaningful, right? Okay, and in this figure what we represent is the pink lines are actually the marginal utilities, the values of the use that we obtain from the inverse optimization problem, that are dynamic because they change with the regressors, okay, with the hour of the day, with this, the outside temperature, etc. And here the black line is the price that is being submitted to the pool of buildings. Okay, here in this table we have the non-flex case and the flex case, and we make a comparison of the different methodologies. What is interesting from this table is that for the non-flex case, you can observe that both the RMAX and the inverse optimization approach that we are proposing, they have very similar performances. And this is actually very sensible, because if there is no price impact, if the price doesn't impact the consumption of the pool, this model here, I mean, if there is no price impact on the consumption, we said that this collapse into this, and the consumption of the pool given by the linear programming problem is just a linear regression of the regressor, which is basically an RMAX model. Okay, so they have very similar performance. But as we increase the flexibility of the pool of buildings, the price impact increases, and what we can see is that the inverse optimization approach that we propose is giving much better results than the classic time series model, where the relationship between price and consumption is linear. Okay, so now I'm going to quickly explain how this can be used and why I'm going to explain why we are interested in this optimization approach, if there are so many tools out there that are probably even offering even better performance forecasting performances. Okay, why inverse optimization? And the reason for this is that we have to think about electricity markets. And in the electricity markets, what we want to do with the pool of consumers actually to take their flexibility and to bring into the market. So we have this aggregator, and this aggregator has a pool of flexible consumers, and this aggregator wants to make money based on the flexibility provided by this pool of consumers. So he or she wants to go to the day-ahead market and to the balancing market to make some money out of this flexibility. Okay, so if we just look at this linear programming problem from a market perspective, this linear programming problem is basically a simple, what we call a simple bid to the market. This is actually what we do to offer in the market, to bid in the market. We present a bidding curve that is constrained to be concave. So this linear programming problem is basically a bid to the market. This is the information that the aggregator has to submit to the market to sell the flexible consumption, to make money out of the flexible consumption, in such a way that we can go a little bit further with inverse optimization. We can think of, instead of a simple bid, we can submit to the market a more complex bid, for example, something like this one. What is a more complex bid? If, for example, we don't only submit the bidding curve, the concave bidding curve, a stepwise bidding curve, but we also submit, for example, some ramping limits to the market, like what they call a pickup limit and a drop-off limits of the flexible consumption. So we can make our linear programming problem more complex to represent complex bids that are being submitted to the market. Like, for example, this one. Okay, here, as opposed to the other model that I have shown, that I show, in this model we are introducing dynamics. I mean, the model itself is coupling different time periods based on these ramping limits. This model, for example, is more suitable to predict the consumption of the pool of consumers over one day, over 24 hours, like, for example, we have to do in a day-ahead electricity market. We will have to submit a bid for the 24-hour market horizon. Also, we can generalize the estimation problem that we need to solve. What I presented here is just one possibility. This one here is just one possibility where we are actually minimizing the duality gaps. But we can generalize this estimation problem. There is no need for us to minimize the duality gap. We can think of other metrics. For example, we can pose our estimation problem in general as a bi-level programming problem where we have to decide on the parameters, we have to decide the value of the parameters of the consumer's price response model, which is this linear programming problem that I show here, this one here. So this one is the lower level problem of a bi-level programming problem in such a way that the upper level problem is deciding on the values of this piece, this R and this U, in such a way that we want to minimize another metric that is not necessarily the duality gap. It could be also, for example, the discrepancy between what we observe, what we measure, and the consumption that is given by the lower level problem, is what I'm representing here. Okay? This is a different case study, and it's, this is based on empirical data, on realistic data. And this is for one day where we try to predict the consumption of the pool of consumers. This pool of consumers here is composed of 27 households, also equipped with heat pumps. And they belong to an experiment that was carried out in the Olympic Peninsula from May 2006 to March 2007. Okay, these 27 households, they have like a smart equipment, a smart control equipment that decided on the consumption of the households based on some occupancy modes, whether the house was empty or not, comfort settings, and also the electricity price. Okay, this is just to illustrate a little bit the type of data that we work with. This is the load for the month of December 2016. The load, it's a very complex data set because it's kind of weird. We have, for example, this is the price that was sent out to the consumers, and we can see that there are periods with high volatile price followed by periods with low volatile price. We can observe also in the data that the load is actually dependent, is correlated with the temperatures outside. Okay, and we did a comparison. Very similar to the one that we did before in the other case study. We have a classical time series model, and the reason why I'm illustrating this case study is because here we also compared with another inverse optimization approach, which basically works, uses as the P bar, P upper bar, and the P lower bound the physical ones. In this problem here, okay, one reasonable value for the power bounds is the actual physical bounds of the houses. We know how much capacity, how much power capacity each household is able to demand, right, from the network. This is given. Okay, so we compare here with this simple inverse optimization approach, where the only thing that we are estimating is the marginal utilities, and the power bounds are fixed to the historical maximum minimum values that we have observed from the data. The conclusions are pretty much the same. Perhaps the most interesting conclusion here is that there is a lot of performance that can be gained by estimating from the data not only the marginal utilities but also the power bounds. So fixing the power bounds to the physical values of the households statistically doesn't work well. So the best thing is also to estimate these power bounds from data. Okay, here just I'm illustrating how the marginal utility changes with time. For example, these 2 different days, and these are the mean marginal utilities that we estimate from the data. For this day, for example, we estimate a marginal utility that is more placed towards the lower consumptions than in this case, because we are receiving a lower price in this place, and our consumption, the consumption of the pool of consumers, is also lower. And yeah, and these are similar results for different months of 2006 and 2007. Just as a conclusion, just to finish here, just to say that there are other, as I said before, there are other methodologies that are working very well. Probably deep learning with neural networks and so on is able to forecast the load very well, the price responsive loads. Maybe other traditional methodologies. For example, here there is a very good methodology to forecast by Hoskin, to forecast the consumption of price responsive loads. I think, as far as I remember, they are using a hierarchical Bayesian approach with splines and very sophisticated technology. And I have to say that we are getting very similar performance results, but with one advantage, which is very important for these to work, which is that as opposed to their methodology, our estimation problem, our model can be directly submitted to the market can process it, and therefore can exploit the flexibility of pool of consumers. In other words, we cannot submit, right now, today, we cannot submit an artificial neural network to the system operator and say, okay, this is the artificial neural network, given the flexibility of the pool of consumers, and you dispatch our loads based on this artificial neural network. This is something that we cannot do today. We have to present information in the form of bits. So that's basically it, because I'm going to skip this. Well, by the way, this is based on 2 papers that are here, just in case you want to go deeper into this topic.
Just a maybe silly question. You have this feasibility and optimality problems. Don't you think there would be a way to merge the two?
Yeah, the merging of the two is actually this bi-level programming thing. Here you are doing the same thing at the same time, but we try to solve this bi-level programming problem like for several months, and it's almost impossible. It's giving very bad solutions. I mean, I think from a statistical point of view, it's better to use this sequential 2-step procedure, solution procedure, than using this bi-level programming problem just at once.
I mean, if you write it as a bi-level, that means you expect an equilibrium between the solution of the 2 problems. So here, if you do it sequential, it's kind of one shot, while you could go back maybe and get something better and iterating? Or?
Yeah, I mean, the thing is that, okay, we try to solve this using very relaxation techniques directly and so on, and we couldn't solve it because this is for online prediction. So we are predicting 1 hour ahead or 1 day ahead. So we need like quick results. But also from a statistical point of view, I think it's better. It's better for the data to decide which value of k is the best that you can choose. Is the best that is the one that is giving you the best performance.
All right.
So about you cast this problem as estimation problem. You don't really specify any randomness in the price. That's the information you have to make an estimation, right? Is that, do you consider it random, or you treat it as a deterministic problem?
The price we consider as a stochastic process.
But in your estimation, do you?
In the estimation, I don't know if in one of the possible, one of the line of future research that we are working on right now is to consider that there is noise in the observations. I don't know if you are talking about that.
No, just the price itself. Do you consider as a deterministic sequence?
Ah.
Or you consider it's a random process?
Okay, but
or realization of random process?
No, we consider that the consumers are receiving a price, a series of prices that are given. That there is no, they are not going to be changed.
Right, but in estimating parameters of the optimization, do you consider prices are realizations of some random process?
Yes, that's it. Yeah,
You don't really
in the
use
same
that.
way. In the same way that when we are estimating the classic time series model.
But you are not using that information in your estimation, right? There is nothing in your estimation that actually use some properties of the distribution.
No,
Another question is,
I mean, no, we are not using any prior knowledge about the prices except the one given by the observations.
okay, that's equivalent to say you don't really
Okay.
model it. So, is there a uniqueness issue? Like, if I just give you a sequence of price, can you say something about the parameters you want to estimate, the P's, and are they uniquely under what kind of scenarios they will be uniquely determined?
No, what we have seen, I don't have a theorem or something like that, but what we have seen is that there could be several values of k, for example, for which we are getting very similar forecasting performance. So probably there are multiple solutions for the parameters or something like that. Okay.
Yes, verification. It's not very clear for me. So you are computing the utility function that is depending on t, and then you are sending that to the market. But then, yes, it's not very clear for me.
Yeah, I use the term utility because it's a way to explain. But you should say it as a bidding curve. When you want to submit, when you want
It will
to.
be different. Perhaps if you are, more or less, it's very connected to the previous question. If you have no volatility on the price in the past, you compute something, and then the price on the market will be something else. And
No, but I mean the way this works is that you submit. I don't know if I understand your question. You submit this information to the market. I mean your bidding curve, how much I want to consume based on the price, together with the power bounds of my bidding curve, or even other information such as rapid limits.
Whatever the price.
No, the price comes afterwards. Then you submit that to the market clears, the price comes, the price is given, and then hopefully your model is good enough to have predicted well what you are going to consume. Right? So the idea is that your bid in the market should reproduce what you are going to consume based on the price.
Your estimation is based just on the price that are realized, so it's not very robust, perhaps, to some. I'm not sure. So anyway,
I mean, if we have enough data with enough
you need to
with enough series of prices, you are going to capture hopefully you are going to capture the behavior of the consumption, how much you are going to consume for a range of prices, but based on the dynamic conditions.
I have another small technical question. I don't understand why you don't have this complementary slackness constraint somewhere.
It's because the complementarity slackness are the strong duality conditions. The strong duality condition is replacing the complementarity slackness. It's a linear programming problem, so you can just enforce the strong duality condition.
Okay. Because you don't. Well, yeah. Okay. Even in the case of your, I don't know. Anyway,
Even in this case, because as long as it's a linear programming problem, we have the strong duality condition, which is the same thing, essentially the same thing as complementarity slackness.
Well, to continue on Patrick's observation, you identify a model of demand response users, but this model has some variability, and so it would be interesting that the output is not a sequence of values or the alpha model exact values, which are not really what happens, but those values with confidence bounds or uncertainty bounds.
I mean, the
I
idea.
think for the operator, you will never assume that your cluster of users is behaving exactly as this estimated model.
No.
It will estimate like
Yeah,
this.
the idea of this is to make it online and to make it adaptive. I mean, once you are getting more information, you have to estimate your model.
That's not my point. I don't think that by having more information, you will remove the uncertainty.
No, that's for sure.
There is an inherent uncertainty on how this cluster will behave. By having more observation, you will have a better capture of this uncertainty, but this uncertainty will remain as in it is important to quantify.
Yeah, but here in this, as I said, this is an ongoing work, so we are not doing here uncertainty quantification. So we are here not saying this is the uncertainty in my parameters and this is the uncertainty on the predicted consumption. Here we are doing just point forecasting. Okay, I mean the next step, we don't know yet how to do uncertainty quantification based on inverse optimization.
Yes, in your study, so there is another parameter than the K is the number of blocks, right?
The number of blocks, yes.
So how did you fix them?
We fix it because this is fixed by the market normally. So that's what we did. I mean, this is everything here is oriented by market bidding. So I think we put 20. I don't know if was the number of blocks that you're allowed to submit in the Nord pool or something like that. But you have a number of blocks that you can submit to the market.
But if you would increase the number of blocks, I guess you can have, in principle, a better.
Yeah, in principle, yes.
And then you can have also overfitting.
You can also have overfitting. Yeah, of course. If you increase the number.
Depending on what you want to do, I mean, the number of blocks is still a parameter.
It's still a parameter, and the model will be sensitive to the number of blocks. As far as I remember, if you put a very low number of blocks, the performance degrades quickly, and if you increase the number of blocks, the performance degrades also because there is overfitting. So you need a mean value. But I think from a practical point of view, the best thing you can do is just to be aligned with what the market is going to allow you to do.
I think this is just an upper bound. I mean, you could have less blocks. I guess the market.
Yeah, of course, maybe your relationship, your price sensitiveness to your sensitiveness to the price, can be described by 3 regimes, by 3 blocks or something like that. Yeah, you can do that. I mean, it depends on the actual relationship between consumption and price.
So if you actually close the loop and your bid is accepted, the outturn at the end of the period will either be higher or lower than you bid. So there'll be a discrepancy between the bid and the outturn. That there is a risk that is carried in terms of whatever penalties or benefits associated with over or underperformance. Why in the real world would you not return to the control systems the information about the risk or penalty they were running in their response?
Yeah, I mean, it is true that here the idea is you submit the bid, the market clears, you receive the price. The price goes. The price is linked to a predicted consumption, and there will be a discrepancy between the predicted consumption and the real consumption. Okay, and there is an asymmetry in cost in how these deviations are priced in the market, right? You could also reformulate this estimation problem in such a way that in this objective function, in the objective function, you can the metric that you can use can be a function of the price for the deviations, for example, in such a way that you estimate the model to minimize the cost of the deviations that you are going to have in a subsequent stage in the balancing market, for example.
Much.
Okay.